Now we're ready to begin to start solving our 1 degree of freedom systems. We're going to begin with the simplest form that we can encounter, an undamped system with free vibration. So we want to start with, what do these systems look like? So after the modeling step, we are at our equation of motion step. We have the ODE that is determining the behavior of our system. And what we're going to see is an equation of motion that looks like this. We have an x double dot term, we have an x term, and then the right-hand side is 0. So when we encounter an equation of motion that's in this very general form, we can conclude a couple things about it. So it's second order, the highest derivative is this double dot term. It's linear, we have an x double dot, but just to the first power, and x to the first power. There's no roots, there's no trig terms, there's no variables multiplying each other. So it is second order linear. If we look at the right-hand side here, it's 0. We have no forcing. There's no explicit t term on the right-hand side. X is a function of t, but those are on the left-hand side. So it's autonomous or free vibration. And if we look at the form here, we have an x double dot, we have an x. We have no x dot term, so there is no damping in this system. So a system like this might start as mx double dot plus kx, and we can rearrange it so it's a little bit easier to identify some of our parameters. We can really just divide everything through by the m, and we'll get x double dot plus k over mx. We can also rewrite that k over m as the omega n squared, the natural frequency squared. And we have to be given some initial conditions here, so some initial position, which we're generically going to call x naught, and some initial velocity we'll call x dot naught. So again, what we're going to be doing in any equations we're trying to solve, any equations of motion we're trying to solve, is we're having some very general form like we're going to see here. And once we identify the type of system we have, we're going to identify what the general solution is going to look like. And then we're going to need to find the specifics based on our exact system. So what we're about to see is the general solution to any system that looks like this. But we're going to have to identify for our particular system, what is the natural frequency of the system we're dealing with? What are the initial conditions we're dealing with? So first, we want to look at the natural frequency. Right, so the natural frequency, as we can see above, is going to just be root k over m. And this is going to be true in any 1 degree of freedom system. The natural frequency is going to be root k over m. If it's damped, if it's undamped, if it's forced or free, this will be the natural frequency. What we want to be very careful of is this is only true in 1 degree of freedom systems where we have one natural frequency. Once we start looking at 2 degree and higher systems, this is not going to be true. This is not how we're going to find the natural frequency in our system. What we'll see is that it's an expansion of this. It's going to be a more general form of this, but there is no one spring constant or mass in higher order systems. So typically, anytime we're dealing with a 1 degree of freedom system, we are going to want to find its natural frequency among other parameters. Okay, so we have this second order system. So what we are interested in is finding that general solution for this ODE. So typically, when we are dealing with ordinary differential equations, we are going to find a homogeneous solution, and we're going to find a particular solution, and we add those together, and we're going to get our total solution. Now, in this section where we're dealing with free vibration, our right-hand side of the equation is always 0 in free vibration. So we have the situation where our total solution is the homogeneous solution. There is no particular solution because there is no forcing. So in these free vibrating scenarios, we only need to find this homogeneous solution. Now, as we saw before in our ordinary differential equations class, we have a general solution that's going to work for systems that look like this, where there's an x double dot and an x term, but there's no x dot term. When we look at damped systems next, the general solution for those is going to look different. But this is one of the first second order systems you certainly saw in your ODE class. And in that class, we saw that the general solution for x of t, the solution to this equation of motion or this ODE, was in this form. It was some constant times a cosine term plus another constant times a sine term. And both the cosine term and the sine term had an angular frequency of the natural frequency. So that's why calculating it is going to be important, because it's going to come into play in our solution. So we can calculate the natural frequency based on the parameters in the ODE, and then the C1 and the C2 we have to find using our initial conditions. So we have two unknowns, we have two initial conditions, we can solve those algebraic expressions for those two constants, and then we have our total solution for x of t. We're going to know the position of this system at all points in time. Now, this is a mathematical solution to this problem. However, it's not going to be quite as intuitive as putting it into another form. So notice here I have a cosine omega t, or omega nt, and a sine omega nt, and then two unknown coefficients that I will find via the initial conditions. For the purposes of this class, I actually want to express my x of t in a different form. Instead of a cosine and a sine, I would rather express this in amplitude and phase form. So I'm going to rewrite my x of t in this form, where I have some amplitude times a cosine omega nt minus phi. So I was able to combine that cosine and sine term into just a cosine term the way I'm presenting it here, and I'm adding, though, a phase phi. So I'm not going to go into the details of mathematically how we make that conversion, but we can. We still have two things we don't know, the amplitude and the phase, but we have only a single trig term, this cosine. So mechanically, intuitively, this is going to make a little bit more sense, because we can see, okay, well, the maximum the value of this function is ever going to be is a plus or minus a, negative a being the minimum, and then there's going to be some phase of theta involved. Whereas if we look at the above form with the cosine and the sine term, we don't really get as good intuition as to what's the amplitude of this response going to look like, and we can't see the phase there. So this solution is mathematically just as good. It just involves some replacements. There's a link to how we do that replacement in the video notes and on the website. So we still have the problem of we have this unknown amplitude and phase now, but again, we have the two initial conditions to find these two unknowns. So we can go through the steps and we can find what the values of a and phi are going to be. And I'll go into detail in the next video of finding these. So the amplitude we are going to find based on the initial position, the initial velocity, and the natural frequency with this calculation. And note with the way I'm solving it here, a is always going to be positive. I'm taking the square root of a positive number is going to give me strictly a positive number. However, the way I find phi, now I want to take the four-quadrant arctangent here, because if I look at the argument of it in the numerator, this initial velocity could be positive or negative, so the numerator could be positive or negative. And if we look at the denominator, the natural frequency is strictly positive, but the initial position could be positive or negative, making the denominator positive or negative. If we just took a regular arctangent here, it's just going to look at the quotient, is the quotient positive or negative, and then give us a value between negative 90 and positive 90 degrees. By doing the four-quadrant arctangent, now it's going to look at the sign of the numerator separately from the sign of the denominator, and it'll return an angle measure from positive 180 to negative 180, or 0 to 360, depending on how the arctangent function, the four-quadrant arctangent function, is set up for you. Now, it's important to use the four-quadrant here because, again, if we look at how this is composed, a is strictly positive, so if, say, our initial position has to be negative, that's going to be reflected in the value of phi over here. So phi can be a positive or negative value. The way we solve for a, it's strictly positive here. But when we put this all together, we can get this product to be negative initially, and it can oscillate between a positive and a negative, and will oscillate between a positive and negative value. And again, the way that this is put together, notice the argument of the cosine is omega nt minus the value of phi.